So here's how we define the hyperbolic functions. Sinh of x is equal to e to the power of x minus e to the negative x all over 2, and cosh of x is equal to e to the power of x plus e to the negative x all over 2. These functions are defined in terms of the exponential function, and they're written as sin h and cos h, like the sine and cosine functions with an h at the end, but one way to pronounce them is sinh and cosh. I'm not going to get too much into the geometric aspects of these functions, but I'll provide a brief overview. Hyperbolic functions are considered the analogs of trigonometric functions, but instead of being defined in terms of the unit circle, it's defined for the unit hyperbola, which I'll introduce in just a second. Hyperbolic functions also have a lot of similar properties and identities to trigonometric functions, and their derivatives are also reminiscent of the derivatives of trigonometric functions, which is why the naming convention is very similar to trigonometric functions. So let's look at this graph. The graph shown is the one for the equation x squared minus y squared equals 1, which is called the unit hyperbola. This equation is implicit, and notice how it's also not a function since it wouldn't pass the vertical line test. The graph intersects the x-axis at x equals 1 and x equals negative 1, and the curves also approach the lines y equals x and y equals negative x asymptotically. So suppose we have a unit hyperbola as pictured, and we construct a line between the origin and some point on the right-hand side of the unit hyperbola. If we define the value a as 2 times the area between the line, the hyperbola, and the x-axis, then this means the area contained within is a over 2. If this is how we define a, then the point where the line meets the hyperbola has the coordinate cosh of a, sinh of a. It turns out that if we define sinh of a and cosh of a in the way we did earlier with the exponential functions, this geometric property always holds for all real values of a. Notice how we're using the variable a for the input of the hyperbolic functions because we've already used x for the equation of the unit hyperbola. If we have negative values of a as the input of the sinh and cosh functions, we treat the a over 2 area as a negative area, similar to negative angles on the unit circle in trigonometry. A negative area is defined as the area a over 2 residing under the x-axis as shown in the diagram. When this is the case, you can see in the diagram that cosh of a still has a positive value, but sinh of a has a negative value. So here's what the graphs of sinh of x and cosh of x look like. You can see that sinh of x is positive for positive x values and negative for negative x values, and takes on a value of 0 when x equals 0, which means the graph passes through the origin. Cosh of x, on the other hand, always has a positive value and takes on a value of 1 when x equals 0. Another thing to note is that sinh of x is an odd function, while cosh of x is an even function. Let's talk about how we can evaluate certain values of hyperbolic functions. If we wanted to evaluate something like sinh of 0, we just plug in 0 into the function definition we introduced earlier. Since sinh of x is equal to e to the x minus e to the negative x all over 2, sinh of 0 is just equal to e to the 0 minus e to the negative 0 all over 2, which is equal to 1 minus 1 all divided by 2, which is just equal to 0. Similarly, since cosh of x is equal to e to the x plus e to the negative x all over 2, cosh of 0 is just equal to e to the 0 plus e to the negative 0 all over 2, which is equal to 1 plus 1 over 2, which is just equal to 1. If we have something like sinh of ln of 2, that's just equal to e to the power of ln2 minus e to the negative ln2 all divided by 2. So the first term in the numerator is just 2, since the exponential and logarithm cancel out. And for the second term, we can rewrite e to the power of negative ln2 as e to the power of ln of 1/2 using logarithm rules, and all of this is divided by 2. Well, this is just equal to 2 minus 1/2, since the exponential and the logarithm cancel out, and this is all divided by 2. And then this is equal to 3 over 2 divided by 2, which is just equal to 3 over 4. So here's what the sinh of 0 and cosh of 0 would look like on a graph. The value of a in this case is 0, which means that the area, a over 2, also equals 0. The only way for the area between the line that goes from the origin to the hyperbola itself and the x-axis to be 0 is if the line goes from the origin to the point on the unit hyperbola where y equals 0. This means the line lies entirely on the x-axis itself. You can see that when the line is constructed in this way, the area is 0. Since the equation of the hyperbola is x squared minus y squared equals 1, and we're considering the point where y equals 0, we can plug in y equals 0 into the equation and get x squared minus 0 equals 1, which implies x equals 1. We are ignoring the case where x equals negative 1, since we defined hyperbolic functions to be on the part of the hyperbola where x is positive. So x equals 1 and y equals 0, so the point where the line meets the hyperbola is 1, 0. And the point always has the coordinates cosh of a, sinh of a, and in this case a equals 0, so we can conclude that cosh of 0 equals 1 and sinh of 0 equals 0. So now let's define the tanh function, which is sort of like the hyperbolic version of the tangent function. It's written as tan h, and one way to pronounce it is tanh. The definition of tanh of x is sinh of x over cosh of x, and this is similar to how tan of x is defined as sine of x over cosine of x. So we know that sinh of x is equal to e to the x minus e to the negative x all over 2, and cosh of x is equal to e to the x plus e to the negative x all over 2. So we can plug the function definitions into the expression sinh of x over cosh of x, and rewrite the expression as e to the x minus e to the negative x all over 2, and all of this is divided by e to the x plus e to the negative x all over 2. We can simplify the complex fraction by multiplying both the numerator and denominator by 2, so this simplifies to e to the x minus e to the negative x all over e to the x plus e to the negative x. So this is tanh of x defined in terms of exponential functions. Here's the graph of tanh of x. It takes on positive values for positive x and negative values for negative x and passes through the origin. It also asymptotically approaches the line y equals 1 for positive x values, and approaches the line y equals negative 1 for negative x values. So this means the range of the function is between negative 1 and 1, non-inclusive. It's also an odd function. So if we wanted to find certain values of tanh of x, we also plug in the value into the function definition of tanh of x. We could calculate sinh of x and cosh of x separately, then find the value of sinh of x over cosh of x, but it's easier to just use the definition of tanh of x with the exponential functions we found earlier. So since tanh of x is equal to e to the x minus e to the negative x all over e to the x plus e to the negative x, if we wanted to find something like tanh of 0, that's just equal to e to the 0 minus e to the negative 0 all over e to the 0 plus e to the negative 0, and that's just equal to 1 minus 1 over 1 plus 1, and that's just equal to 0. If we wanted to find something like tanh of ln of 2, that's just equal to e to the ln of 2 minus e to the negative ln of 2 all over e to the ln of 2 plus e to the negative ln of 2. The exponential and the logarithm cancel out, so e to the ln of 2 is just equal to 2, and we can rewrite e to the negative ln of 2 as e to the ln of 1/2 using logarithm rules. So in the denominator, e to the ln of 2 is also equal to 2, and then plus e to the negative ln 2 is just the same as plus e to the ln of 1/2. So then the exponential and the logarithm cancel out again for the expression e to the ln of 1/2. So this is just 2 minus 1/2 over 2 plus 1/2. And this is just equal to 3 over 2 over 5 over 2. And if we simplify this complex fraction by multiplying both the numerator and denominator by 2, this simplifies to 3 over 5. So to summarize, the hyperbolic functions sinh of x and cosh of x are defined in terms of exponential functions. The function tanh of x is defined as sinh of x over cosh of x, and we can rewrite this in terms of exponential functions using the definitions of sinh of x and cosh of x.